Hi guys, so today the plan is round 678, pretty simple. We're just gonna get into it, and actually I forgot to do this for a while. I'm gonna update the sub count to what it is now. It's still an insane number. Yeah. That was last Wednesday, I believe, that I updated it. But yeah, let's get oh shoot, I just missed the link. Whoops. Okay, that was a mistake. I'm gonna have to take a while to load that now. Enter. Guess now I can open all the problems at the same time. C is called binary search. Alright, that's gonna be fun then. Okay, given array and integers, m, while text not loading, possible to reorder elements such that the sum of all I and all j of aj divided by j. Wait, what? Oh. Is equal to m. Come on. Why is this not loading? This is weird. Okay. If I equals 1, j equals I. Oh. Okay, so basically, I think the way this works is consider element x. Then every element that's a sum before, every element that comes before x is going to include x over j in this sum. Which essentially means that what does it mean? It means that, so you, each time in the sum you get x over j, but you also have the position, like this is j, because this is its position and there are exactly j elements that included in their sums. So this element is going to be included in the total sum j times x over j times, which means that essentially, so imagine the total sum of the array, because automatically that's going to be included, and then subtract it with the sum of ai modulo I. And I guess the question is, can you make it so that sum exists? And I don't know how to do that. So it's floor division, right? Oh wait, no rounding. Oh wait, no rounding. Okay. So it's just, oh. Okay, so this part is actually, wait. Okay, yeah. This is stupid. There's no rounding. So this is just straight up the sum of x, which means that no matter how you order the elements, the sum is going to be the same, because each thing is included j times x over j times, which is just itself. Yeah, okay, sure. Nice, good problem. Fun problem. What? Test cases. Did not copy the input. Yes, no, because you literally just check if the whole sum is m. Okay. And so obviously because you can't change the sum, if the initial sum is equal to m, you're already done, and if not, then there's nothing you can do. Prime square. Magic squares have already been studied by hundreds of people, so he sees no sense of studying them further. Instead, he invented his own type of square, a prime square. Square of size n times n is called prime if the following three conditions are held simultaneously. All numbers on the square are non-negative integers. There are no prime numbers. Sum of integers in each row and each column are prime numbers. Sum of integers in each row and each column are prime numbers. What's with the Q? That's kind of scary. How long has this been going on? Is this gonna make the round unrated? That'd be unfortunate. Has it judged anything? Hasn't judged anything. All these have been running for... what the hell? It's kind of sad. Slightly a glitch, okay. Well, I hope I did that right. I did do it right? Like you subtract m and then you print if the sum is not 0, then it's no, otherwise yes. I don't know why I didn't just do something normal, but whatever. So there are no prime numbers in the square. Well, submissions will be soon judged. Okay. Have faith in Codeforces, guys. They'll fix stuff, even if something's going wrong. Okay, what is happening here? So let's say n is prime. Oh, n is 100. Oh, that's fine. Yeah, of course it would have to be, actually. N is prime. If n is prime, we can just print all ones. Otherwise, there's some other thing that has to go on. And my general idea right now is you have the matrix. You have the matrix, and you put in some integer, for example, 2, in all of these squares. And then on the main diagonal, you put some number x in each of these, where x is not prime. But, no wait, actually 2 is prime, so let's not do 2. Let's do 4, for example. Or just 1, actually. That works better. Because they say 1 is allowed, because 1 is not prime, supposedly. So, and then we put some number x on the main diagonal. And the important thing about the main diagonal is that it affects exactly every row and every column has only one x in it, because the main diagonal has effect on exactly one row and exactly one column. So if we can just find an x, that isn't prime, but m minus 1 plus x is prime, then we're done. And like this just has to exist. I mean, primes are sparse, yes, but... and then x composite. Like this kind of just has to exist. And that's my idea. So, I'm gonna copy in my number theory template, which I still haven't fixed somehow, so I gotta do that at some point. Basically, I'm just using it for gem primes. For L equals 2. Sieve. right? Does this compile? I really need to fix this, honestly. I don't know why. I've told myself to do that like 3 times now, and I haven't done it yet. Just procrastination at its finest. Has this judged yet? I hope I can successfully find... Okay, there we go. I would hope I can successfully find the sum of an array. Okay, right? But like, there's no reason that this wouldn't exist. You know, primes get like more and more sparse as you get higher, and so I would just imagine that there isn't a problem with this. And okay, let's see. So, but what we can do is just do it for like all of them. All right. So for 2 I is less than or equal to 100, I plus plus. For j equals 0, right? J equals 1, j is less than or equal to, I don't know, some big number. So what we're checking is if not prime, I'm just verifying this with a program right now, and I minus 1 plus j basically just checking if we can do this for all possible inputs. Can and we can. So basically all this is checking is that for everything there exists an x such that x itself is not prime, but m minus 1 plus x is prime. So that means that this construction, where we put 1s everywhere except the main diagonal and find some x, will work. So now let's just do it. So let's see. M minus 1 plus j. That works. And then we'll just say x equals j. I guess there's a better way you could do it. We can like put zeros or something, but whatever, it doesn't matter that much. Actually, we can end up doing some construction where we put zeros on the main diagonal, and so every column ends up with exactly k zeros. And then we just need a number less than or equal to n that's prime, and that would work too. There are probably a lot of constructions that work. But I'm doing this one because I don't know. From j and not from x equals j, mat ij equals x. Then we just kind of like print it, which I don't even know why. Alright, I equals j, see out. I don't even know why we're doing all that. And then print new line. One, 7, looks right. Okay, this is slightly slow, but whatever. How's the Q doing? Okay, whatever. Andrew thinks he's truly a successful developer, but he didn't know about the binary search until recently. After reading some literature, Andrew understood that his algorithm allows to quickly find a certain number x in the array, and do even more things, but sure. From an array A, next from 0, pseudocode, yeah. Only works if the array is sorted. Huh. Okay. Well, that's fun. So we're interested in the number of permutations where the binary search algorithm finds X. What is left plus right? Is it floor division? Yeah, running down, okay. So n is small. That's kind of important, I think. Because it might be like required to kind of brute force this thing. Okay, so like what I'm thinking is consider the first position where like say you have an array like a nice array where everything divides nicely, then the first thing you're going to query is this. And so whatever number you have here, it's going to take you into some side of it. So let's see, there are okay, so if we ever touch X at all, we'll find it in the algorithm because that's just how this works. But otherwise, so we query the middle, and so right is an exclusive bound. So we start off with this bound, including here, excluding this. And then we query this point, and we ask if it's like less than or equal to X. If so, we move the left bound to here. And then we check if this is X, and if it was, then we're done. And otherwise, if it's not X, then we'll continue in this range, and otherwise we will move the right bound to here, exclusive, which means that we're only looking in this range now. And then we continue. So there are three possibilities for what we put in this position. It's a number less than X, equal to X, or greater than X. And there's a certain like probability of all of those happening. Or actually, there are like a certain number of numbers. Like obviously this is x minus 1, this is 1, and this is n minus x. Yeah. So essentially we have this like function, like say f of n, where we're working with the size of array n. And then on one side we split, if this is the case, we split into this, and if this is the case, we split into this array. And so now we're working with kind of a smaller array where it doesn't really matter what we put at the other positions. It's more like it's more just like what happens at this point, I guess. Well, so say we do have a number less than x, then the binary search is going to go into here. So whatever we do here doesn't matter. We'll just kind of ignore it and then fill in the rest of the numbers in the end. So now we care about this range, and Okay, I think it's kind of more like f of n and then like another parameter x, where n is size and x is the remaining range, or the number of numbers that are remaining. Okay, sure. What is this? So 1005. It's like, and then the modulo is something 10 to the 9th plus 7, they said. So there are three possibilities. The first is that we do x minus 1. Does the parity matter? It does, doesn't it? Yeah, it kind of does, because it depends on where we do the midpoint. That's annoying. Actually, does it matter? But maybe it doesn't. Let's say you have like 3, 6 versus 4, 7. This is going to map to 4. I guess it doesn't. Okay, fine. So that makes it easier. Although m equals, let's see, so it's just floor n over 2, right? We have 1 to 5, 0 to 4, n plus 1 over 2. Because we assume we have the range of 1 and n, and therefore we want the midpoint of that, which is L plus R over 2. So left equals m minus 1, right equals n minus m. And so, all right, if dpn x is not equal to -1, if n is less than 0, n is equal to 0, and there's no way to do it, I guess, and x won't matter because n will decrease faster. I assume we don't actually have that many states, but I'm not really sure. Ants plus, let's see, left times f of left and x plus 1. This is if we go to the left. Actually, let's define x to be n elements left to place, because that's easier. So now we can do x minus 1. And otherwise, if we put, so we have x minus 1 ways to go into the left. We have n minus x ways to go into the right. And otherwise, we put x down directly, and that's simple because it's just, like it's 1, because you have one element, and then the remaining elements are x factorial. Fact x minus 1. I feel like this might overcount. I'm not really sure. Let's just kind of test it. How this should, yep. Wait, there's a required position? Oh, that's fun. Okay. Wait, that's actually easier then. So, okay, that is easier then. Imagine misreading a problem and then writing a solution for that misread problem. All right, this is not my day. Let's just keep going. So this is like, does this make it easier? It should, right? You kind of just like go through it, and then you say, that's kind of just it actually. Like if you have a position P, then you need a number less than X for this to happen. And if you're like querying here, for example, you need a number greater than X. Okay. Well, that was stupid. I just like totally overcomplicated this. But that's fine, I suppose, because now it's going to be even easier to write. Now we're going to be even more behind on time. Isn't that great? While L equals 0, R equals N, while L is less than R. What did they do? Well, L is less than R. Okay. Okay, I'm just going to explain this after at this point. I'm so behind on time by now. Ants equals X, ants times fact, X equals 1, break. Otherwise, if, let's see, P is less than M, then we want a number less than or equal to X. Yeah, number less than or equal to X, so it's equals ants times LE mod mod. And we assume we use one. Otherwise, we want a bigger number equals ants times the number of greater elements. And if LE or GR are ever 0, then automatically we'll have no ways to do it. And so even if it goes into the negatives, it doesn't matter, I don't think, because we'll have 0 no matter what. What the hell is going on? I don't even know why I compute a whole factorial array. What the hell? Come on. What is even... Can't write semicolons. That should be count. Number of remaining elements. Infinite loop. Oh, yeah, that makes sense. L equals M. Otherwise, R equals M, or L equals M plus 1. I just realized this is like how I do binary search. Why do I not understand this? And that's wrong. Great. What does it get if I want the number of ways to make it be 1? I want element 1 in position 1. A middle. I think I swapped these. That might be it. What? Why is it still now? Okay. Sure. Alright, well that is kind of sad. Whatever. Position doesn't matter anyway, it's not rated. Ideally we don't fail system tests. That would be epic. Bandits appear in the city, so we have a tree. To Sunday walk, all the roads were directed in such a way that it's possible to reach any square from the main square. Okay, so you have a rooted tree, and every edge is directed away from the root. The moment where the bandit appeared on the main square, there were AI citizens. So each citizen currently on a square moves to a child. Then the bandit chooses one of the one-way roads outgoing from the square and moves along it. Okay, so everything's basically optimal, and we're trying to figure out the result of this game, I guess. Are we getting TLE here? Or is it just, like, insanely slow? I'll be extended by 10 minutes, and we'll be rated. Okay. Jesus, come on. It's gonna be a notification for every tab. Alright, this is a painfully weak sample. Citizens want to minimize the number of caught people, which I assume means that they want to distribute things as evenly as possible. um... Okay, so it kind of depends on the number of leaves, I suppose. So we have some subtree here, for example, like this, and with like a ton of edges. How many people have solved C? This is sad. Wait, really? I thought more people would have solved it. Okay. Whatever. So we have a ton of leaves and some stuff going on. And, well, whatever is going on is that this would be easier if there weren't bandits in the first square, wouldn't it? Oh, wait. Oh, he doesn't capture. Okay, that's simple then. So he basically goes to a. So the bandit's gonna go to a leaf and capture all the citizens of the leaf. The citizens want to make it so it's as like little as possible. So imagine this subtree, which has how this works. So it has 3 leaves on the bottom of it, and say it has some like 7 or something. Then the best you can do is 3. Like that's the minimum. That's the minimum answer. But at the same time, say it's distributed like this. You have 1 here, 1 here, 1 here, and 4 here, and the answer is actually 4, which is kind of annoying. So either you distribute it as evenly as possible, or you distribute it as evenly as you can, I guess. So say we have some function f of k, or f of, I don't know, something, f of I, which is like the minimum value in subtree I. F of I is the minimum value in subtree I. Okay, now, for example, this. Now, if this is x, and this is, let's use some numbers. If this is 7, and this is, I don't know, 5, for example, and then we have 4 things here. And then this has some 11, I don't know, this has some 10. So the total sum of the tree is 25, and we have 5 leaves. So the worst possible answer is 5. Or like the lowest possible answer is 25 over 5 ceilinged, which is 5. But then we have the subtree with 7 in it already, and so that's actually the worst answer. So the answer is like the, so I think the answer is the max of f of u, where u is an element of the children of I. Either that or the ceiling of the sum over the number of leaves, since that's how it would be if it were optimally distributed. I think that works. Unless I've misread it once again, which is very, 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 very possible. But whatever. Okay. Are there multitests? There are not. There are 2 times 10 to the 5th nodes. Minus x, edges x dot push back I plus 1. This is how we create a tree. Then do some dp. Trying to speed to make up for my terrible penalty on the first problems. So let's do that now. Okay, so n leaf v equals 0. If this is 0, then we want it to be a leaf, otherwise it isn't. Sum v equals ab. And then dp v equals 0. For llx, edges v, n leaf v plus equals n leaf x, or first dfs x. We don't want to go to the parent. Sum v plus equals sum x. dpv equals max dpv. So it would be, let's see, sum v plus n leaf v minus 1. This is ceiling function, and return that. let's see, does this look right? C into n, C into x, minus x, push back, AI, DFS, do the dphi, okay, and so this will be 0 if there's at least one child and one otherwise, that's the definition of a leaf. Then the sum is just the array value, and dp is 0. And we DFS, add the leaves, add the sum, check the max, and then do the ceiling. I don't know. Why does it say this has 30 minutes? Oh, because it got extended. Okay. Alright, well, it's still judging. So the max of a certain array is the smallest positive integer not in this array. The max of mexes of the subarrays. Max of mexes of the subarrays. How are the people doing? Okay. Well, we had a terrible penalty on all of these. Or not penalty, just like speed. Then we're picking it up with D, I suppose. I might try and rush through E also, just to save my rank, you know? Alright, so the max of mexes of all subarrays. What the hell? Alright, let's see if we can ask the question, can the mex be... What the hell is this spacing? Can the mex be I? Or let's say this is the overall mex. And so specifically, we'll ask this question for I in increasing order. Meaning that if we're asking this question for I, it means we've already asked it for I minus 1, and we say it can't because I minus 1 is the max of some subarray. Does that make it easier? I feel like it doesn't. Wait, are there only 7 pretests for D? And people are getting wrong answer on pretest 7. That's a bit sus. I mean, we passed the huge test, so I suppose it's fine. I don't know. Open and find the max of mexes of all the subarrays. Right. So if we ask the question, can the max be I, is this like possible? How do we do that efficiently is the question. So the individual elements here are interesting. Like, consider any element that doesn't exist in the array. For example, say we have like 1, 2, and 4. Then the max of any subarray will be 1 and 2. Which is to say the max will be 3, but then there's no way, wait, is that how that works? There's no way the max of any subarray will ever be 4, because, yeah, there's no way the max of any subarray will ever be 4. Okay, maybe we can binary search on the max. Does that? That doesn't, I don't feel like that works. Because it's not necessarily easier to check. It's true that if the max can't be I, then it can't be I plus 1, and if it can be I, then it... No, it can't be. Like, it's an answer. Never mind, what am I saying? This is more like asking, do the numbers 1, 2, 3, dot, 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 I minus 1 exist? Rather than asking specifically if the max is I. That we can binary search on, but I don't see how that makes it easier to solve. But maybe it does. So consider the first element that doesn't exist in the array. We know the answer is at most, so that number is x, then the number is at most x plus 1. Because you see here, we don't have a 3 here, and so the answer is at most 4. And in fact, it is 4. Okay, let's try something else. So say the max is 2, or say the max is 3. First, you have to have a 1. And should you have that 1, first you have to have a 1. What's the time limit? 1 second. Also, what's our penalty now? I'm pretty sure it's terrible. I guess as more people solve D, it'll go down. I don't know. We had like terrible A, B, and C, and then blazing fast D. Oh wow, okay. LGM my room, nice. So like first you have to have a 1, and then you have to have a 2. So either you have a 2 on the left or the right. Let's say you pick the 2 on the right, and then you have this subarray, and now you have to have a 3. Now either 3 is within this already, or it's somewhere else, I guess. And so if it's somewhere else, I don't know, continue the process? That's doesn't seem like it goes anywhere. I have an idea. Let's say we're asking if the max can be I. Then we're basically asking, does there exist a subarray that's kind of sketchy. Say we know the max can be I, and then we want to know if the max can be also I plus 1, which is again checking if these numbers exist. Then that's the same as saying, is this possible? I really don't know. Thinking DSU. Here, let me stroke this idea of insanity a bit. So say we want to find if the max is exactly I plus 1. Or if there's a subarray with max exactly I plus 1. Then like consider all elements, consider you have some like x's. Where x is less than I plus 1. And then any number greater than or equal to I plus 1 is equal to a y. So you have some array that looks like this with a bunch of x's and y's. And so with this setup, A, longer is better. Longer is better because you already guarantee that no element will make the max higher than it needs to be by setting all of these to y. So the more elements you have, the better of a chance you have of having the max be exactly this. And B, these are contiguous ranges, so we can kind of use DSU to merge them. That is my idea. So if we can say this range has max k, and this range has max m, and then we merge these two together eventually, what do we do? Maybe we don't necessarily need the max, we need the elements. Okay, let's store the max of a set of size k. That max is at most k plus 1. So with a set of size k, we can initially have the numbers Actually, I have a better idea. Okay, I have a better idea that isn't like annoying. So we want to store the max, and all we can use is like an STL set, which is a set of sorted elements where we can use iterators and stuff to access anything. I don't know why I'm doing mostly primes here. Say we have a 2 here and maybe a 4 here. Right, but if we have two consecutive numbers at the beginning, then we know the mex isn't this because we know this element is kind of irrelevant because this element's going to be like bigger. No, this actually should be even easier. What am I saying? Say we know the mex is x. So we know the mex of one of the sets at least is x. Then all numbers less than x are irrelevant. And so now at each point we just need to check if x itself is in the set once we merge, and then if so, we set the mex to x plus 1 and continue. Okay, sure. So this becomes DSU then. And that is doable. And so I'm going to try and blaze through this again because I want to, why do I have heavy light open and whatever this is? Alright, okay. I remember what that was. Okay, so read into n. Now we ask, bool on so the mex is automatically 1, we ask if it can be greater than 1. Let's do the DSU first. So this is more like for LLX vals marks A, vals marks B dot insert X, and vals marks A dot clear. It's the same memory. It's the same complexity as small to large, so it's O of n log squared of n, which I think is fine. Yeah, vals marks B dot insert X, vals marks A dot clear. Maybe I'll be hacked, whatever. the worst case is doable anyway. We erase just to like improve the constant of it, doesn't really matter. And then we increment the max because we can, and we should, because we just found that element. Let's set up the DSU2. So vowels AI to pushback I. Now, D dot vowels I to, we initially guarantee that marks I equals I, so that's fine. If D dot max, D dot marks X is equal to I, cause equals 1. Then okay. Whoops. Now we wait for the wrong answers, don't we? Or the seg faults. Great. Does it work for this one or does it also crash? Okay, cool. Why? I'm set on 0, size of on. What? D dot vowels I to insert AI, D dot remax I. Well, where did we get to? Didn't even get to that part. Didn't get to that part either. Maybe it's just like, what's happening? Oh, there should be max. Whoops. Yeah, cool. And that's wrong. So one's special. So if everything's 1, then like all the mexes are going to be 1. Otherwise, there's something that isn't 1, and therefore we can assume that the answer is at least 2, and then we can start doing things. I assume? Or does it just mean the whole thing is fundamentally flawed? Nice. Guess we could ask about that. Okay. I do not trust this one bit. So, let's try more. Now this mex should be 3. Is that right? No, it's not. Okay. Let's test it once again on the samples with that change. And just look over the code. So read into N, read into AI, check if everything's 1. If so, there's nothing we can do. Otherwise, there's at least one element that isn't 1. So therefore, the mex is at least 2. And if the mex is at least 2, then we can start looking at things. So that's fine. That was AI to push back I. Do.pals I dot insert AI, put it in, remix. Merge with above, merge with below, or merge with left, merge with right. Do.mex. Let me check here. So while the mex exists in the set, increase the mex. Merge small to largely, so that works. Remix marks B. That would also work, right? Yeah. Remix with that, and initially everything's itself. Alright, I believe. It's a bit sketchy, but I believe. Okay, great. Should still be 3, yeah. 1, 2, 2, 4, 3, 4, 2, 1. should be 4 because that 3 is kind of isolated by itself. You can't have a 3 without the 4, so is this a big case or not a big case? Okay, it's not a big case. No, that's wrong, isn't it? Oh, that is wrong, actually. That's not fun, because we want to... Okay, well, I see. We want to split, like, this has max of 3, actually. We want to split only by I plus 1. How do we do that? Yeah, I see the issue. This whole thing can be considered to be one subarray. We just want to ignore the 3 specifically. Ugh, okay. So we can query the max of a subarray, then we'll be done. Is there a way to do that? Is that a thing that exists? Have to be offline. Oh, that's smart. Okay. Guess we can do it offline. Okay, new idea because the old one was wrong, like blatantly wrong. I don't know how I thought it was right for so long, but so scrap the DSU. What we're interested in is, okay, so we want to know if there's a subarray with max x. then we gotta like ignore all the elements with max exactly x, not greater than or equal to, but exactly. That's the problem. The problem is that it has to be exactly, because anything greater isn't going to affect the max, so we can kind of just ignore it. But let's say now we have a bunch of these subarrays, and if we can query the max sufficiently of these subarrays, then we can be done. Why do I do this to myself? Why did I mess this up so badly? This is so annoying. This is very annoying. Don't need DSU at all. Don't even need this. In fact, all we need are the values. So we can keep this because it's a special case. But okay, this is the one that killed me. This answer should be 4. No, 5. Yeah. Alright, so we're gonna ignore this. Basically, we compute this magic possible array, and then ans equals 2. While pause ans. Pause ans. Now we just like do some stuff. We got like a lot of ranges, and okay, that Stack Overflow post that I glanced at for a second is like, it's what you gotta do. How bad is my penalty now? Okay, surprisingly not bad actually. So once we solve E, we'll be in good shape, I suppose, and we're going to solve E because I know how to do this. And I will explain how to do it later, but right now I gotta save myself because my penalty is still gonna be bad now. Okay, now basically we have LL pair LL LL. No, this should be 2. If this is true, then the range doesn't exist because it's the range from last to x minus 1. Then qv dot, or I guess last is less than push back, make pair, or actually I can do the notation, whatever. Doesn't matter in the slightest. Last, x minus 1, pair that with I, because we want to see if I is possible. Right. Last equals x plus 1. Might actually want to do it like this, where we do it by the right point, because that's how we're going to do it eventually. is quite annoying, I would say. I don't even need. Just gonna make the whole thing long, and kind of screw over my own template. So going by that Stack Overflow post, we're interested in smallest value x less than L. Fine. So we gotta do this stupid segment tree thing again. Nice. Just make everything long. Oh my god, this is so annoying the way it does this. I kind of get rid of autocomplete. So this is like no lazy propagation anymore. TL equals TR. Turn tree I equals V. Otherwise, if TR is less than Q or Q is greater than TL, return tree I. It's that condition, right? Yeah, that's fine. Query we do want ranges for. Mid, that's fine, that's all fine. Set the thing to that. See if it compiles. It's not compile. Because we got the lazy propagation, we didn't actually do it. P position. What? No. Don't need DSU anymore. Is this max or min? We want min, don't we? We want the earliest thing where the minimum is less than x. So this should be 1E9 or something. Then, okay, so if TL equals TR, return TL. If tree 2 times I plus 1 is less than V, that means that there's a minimum on the left side. Return BS 2 times I plus 1. No, wait. Into mid equals TL plus TR over 2. So then TL mid V. Return BS 2 times I plus 2. Mid plus 1. TR V. trying to type fast, and you can see what's happening to me. If last AI is not equal to -1, actually this is simple. st.update AI -1 last AI. Yeah, set that position to this. Actually, this should just be I. Actually, we don't need last at all. Nice. So while we have queries and qp dot first is equal to I, that means this is the right point, then x equals segtree.binary search on 0, 0, and -1, and the question is the element less than the left position, which means qv qp.f.f.s. That's the first element that doesn't exist, so pause. Guess we just need that, don't we? qb qp.s. This whole thing is kind of pointless, but whatever. And then plus qb. Does this work? Don't need the DSU stuff. Signed and unsigned is fine. That's not fine. Okay, so what is, print the value before we can compute it. It's either 4 or 0. Nice. Yeah. So these are things that end it. What? That's a bit confusing. So we have the interval 0 and 1, which doesn't make any sense at all. Kind of don't need that extra bit of information, but whatever. So the answer for 0 and 1, there are multiple problems here. I'm going to rerun it just to have it all together. So the answer for 0 and 1 is 4, which doesn't make sense. Don't need query at all. Guess it should be that. No, this should be I. this should be I, not specifically AI, although maybe that doesn't make a difference. Why are we debugging on the harder one? It doesn't fix anything. Okay. So what's with these ranges, right? Like, what's going on here? 2, 1. Okay, that's actually right. So the range 1, 2 is fine. Although the max is actually right. Is it that? Is that the problem? Well, the problem is that all of the answers are like wrong. So 0, 1, the max should be 2 here. Why would the answer be 4? This should not be hard. What is happening? This should really not be hard. This is something I've written like 5 times before. What is happening? Just got rid of query. Wait, what did I change? Okay, I should have query back. This should be vals I. So it should have everything. That. Why would you do that? Why would it all be 0? If I do this, will this work? Doesn't fix anything. Why would it be 0? Oh my god. Okay. I don't understand this. Why is it not splitting by 4? Okay. Does that make sense? Yeah, it does. Okay. So the queries themselves are kind of messed up, but so are the answers. Like, the answers are wrong. Why are the answers wrong? Why would all of this be 0? Like, everything here should not be 0. I just set it up so it's -1. I just set it up so it's -1. And then I touch it. Is this going out of bounds somehow? How would this be 0? Like, get rid of the update. Does that fix everything? Okay, so the update is somehow setting everything to 0. Which makes no sense. Why would it set everything to 0? I must have messed up some of these conditions somehow. I guess. Yeah, somehow. How? What am I? Q. Wait, this should be Q is less than. So that's seriously a problem? That's a problem. Okay, that's better now. Better, but not fixed. Why is not fixed? So 0, 1, 2, 3. So this is, we want to add 1 to this because that's how the mix will work, I suppose, right? Okay. Obviously, I can't trust this yet. Let's test it on some of my cases. Should be 5. Yep, okay. Should not be 8. What's the problem here? Is it this? Why does that happen? So would think the max is oh. If tree I, if the whole thing is greater than or equal to b, then return something outside of that. Okay. Still works. Still works. Make these queries. Don't even need the pair, but whatever. Just wasted information. Not important. For all queries ending in I, do the exact thing that the Stack Overflow says to say, says to do, and yeah. Okay. It's in queue. Okay, well, that was a thing. Got it eventually, though. It's actually pretty good somehow, despite spending so long on debugging. My god. This run just felt terrible. I have no idea how I'm doing so well. This is really confusing. This guy is like IGM from the US. I remember him. Okay, who else? I'm so confused. How's this going so well? Alright, well, do we have the opportunity to solve F? Or all pairs of subsets A and B such that... What the hell? So B is a subset of A. B is the size of A minus 1. GCD of all elements in A is equal to 1. Find the sum of elements in A times the sum of elements in B. And the set is huge and you can't even enumerate things you want to. Okay. Alright. Let's see what we can do here. I'll give it a bit of thought. Well, hacks. Hacks on C. Am I about to be hacked? What is C? Oh, C is that. I don't know. That's kind of sus. What were the other problems? So A was fine. B was like... Right. Okay, I'm gonna go to the bathroom. I'll be right back. I suppose. Let's mute this thing. Alright. So what if, instead of doing that for, what if we do the complement instead? Where we, wait, okay. This mod, this mod scares me, because the other mod was 10 to the 9th plus 7. And so this mod kind of makes me think that you're going to have to use FFT or something for this. That's not fun. Because this mod is like a big power of 2 plus 1 or something. It's like a power of 2 times some prime plus 1 or minus 1, something. I don't know how it works. But no matter how it works, I don't know how to do it. I guess we can think about it anyway. Let's say you have some mod, or wait, so we can try counting the complement, where instead of doing it for all elements for the GCD is 1, we can do it for all elements where the GCD is bigger than 1. That feels easier. Then we can fix the GCD and say that all elements, and then we can fix the GCD, and then we have a certain subset of numbers we're working with. And then once we do that, yeah, maybe? Is that possible? How do we even do it with that? Let's say we decide we have some amount of numbers for each like thing. Wow, there's a lot of notes here. Okay. So we decide we have some numbers like x1 amount, or no, k1 amounts of x1, k2 amounts of x2, k3 amounts of x3, dot dot dot, kn amounts of xn. Then the answer for this group of numbers is this is one specific subset. This is one specific A, and then we're going to count the sum over B's that correspond to this. So this is the sum of ki times xi. That's the first part of this. And then the second part is the sum of, what would it be? So it's big sum over, let's call this small a. Then it's the big sum of small a so each individual subset is small a, except you're going to exclude xi, and you're also going to multiply by ki. Because you exclude a single value of xi. Is there any way to simplify this? Obviously, we can't naively compute this over all subsets. So, is there any way to simplify this? Not many of my friends are doing this. That's sad. I guess it's very, even earlier for the people in Eastern time. What's happened with the people? Pretest 7. Alright, wrong answer on pretest 7. I remember that. Jesus. It's a lot of wrong answers. Yeah, this is not a friendly round for my friends. Okay. Well, what's happening then? Might as well make as much headway on this problem as I can. I'm sure in 17 minutes there's no way I can implement this, especially if it requires FFT or something, but I'll do what I can. Did everyone get wrong answer on this somehow? I kind of like wrote a totally wrong solution and then had to rewrite the whole thing, but it's just wrong answer 3, wrong answer 3, wrong answer 3, TLE 8. Interesting, someone solved only that. A lot of wrong answers. Okay, why am I doing this instead of solving the problem? Come on. We have some time left. So for a fixed A, there's like a thing. So what we really want to do is, given this as the subset of all possible numbers we have to include, we want to solve over all possible A's and all possible B's in O of n, or O of n times like log something. We have 1 second, Jesus. Is this whole thing 1 second? This is 1.5 somehow. So we have n times x, where x is like n. Because then we can do some harmonic series stuff, and that's fine. That's not the problem. The problem is like we have to do this somehow. So the question is, how exactly do we do this? And I don't know the answer, so let's try and figure that out. Indeed, I do not know the answer at all. Okay, what if we instead do something like this? So we fix xi, and we say we want to remove xi. That's not the right. So we want to remove xi, and say del xi, even though del is like a totally different meaning. And this is the element we're going to remove, which means that we have to consider all of the sums of A that contain this, and then we consider this. Although this sum becomes easier, doesn't it? Because it's just... Well, it's kind of a different thing. So we have a set A, and then we're considering over all sets A the set A not A without xi, and that's what B is going to be. So it's going to be ki, because each time if we include xi, we can remove ki instances of it. Is this subset? I actually don't know. Subset, okay. So ki times the value of a but in each value of a we remove a single value of xi. Wait, this shouldn't be, should it be times? I think yeah, it should be. It should be a single value of xi that we remove. Wait, this is, oh, this is a problem. No, this is subtraction. I didn't even realize. This isn't division, this is subtraction. Oh boy, that makes it harder. If it was division, I think it would be easier, actually. But this is a problem. Okay. Yeah, that is a problem. So this would be, it would be like the sum of all subsets that the sets that contain it. Minus a single instance of xi over all possible a. This is over all possible a. And then actually it would be this times a. I don't even think it's this simple actually, because we don't necessarily, oh boy, that is a problem. Because we don't necessarily always have ki instances of, oh boy, that's fun. Okay, yeah, we don't necessarily always have ki instances of xi in a. Does that matter? It's more specifically we solve for a single element in B, and none of the rest of it matters. And then, okay, yeah, we solve for a single element with value xi, and all elements with value xi are equivalent, so therefore we can multiply it by that. And I think so it's ki times the value for an xi. So this becomes, over all possible a, it's the sum of a squared minus a times xi. So this is the sum of all possible a squared, which is even more fun. And then the sum of all possible a times xi. So if we can do that, we'll be good. Maybe? Can't even tell at this point. Can we do sum of a? Sum of a should be simple. So we guarantee that it has xi, which means that every other element in the whole set that we're working with has just like is either included or it isn't. So when it's included, so the normal formula for a set, for example, 2, 3, 5, 7, and then sum over all subsets is the sum, or no, the product of AI plus 1, all minus 1. Because each element, you either take it or you don't. Wait, is the sum of all subsets. No, it's simpler than that, actually. It's that if you have n elements, if you take this, then all the other elements have 2 to the n minus 1 possibilities. So it's the sum, the sum of AI times 2 to the n minus 1. I was thinking of something else, like prime factors or something. So this is the sum of AI times 2 to the n minus 1. So with this, we can compute n, and then we can say that it's the sum of ki times ai, or xi times 2 to the n minus 1, and that's fine. So the sum of a we can handle. The sum of a squared might be a problem. Because it's the sum of the sums squared. So it's the sum of this squared. Maybe that's where the f of t comes in? Make like a generating function or something for this? Well, I don't really know how to do that. The rest seems straightforward enough, but the last part is too hard for me. So I guess we'll call it a day here. Don't really know. Where am I right now? Okay, 44th. That's pretty good. F is impossible! Yay! Impossible for me, at least. Maybe not others. But I mean, okay, even though we had like everyone, a lot of people beat me on A, B, and C. But when we picked it up at D, and then we omega bricked on E. Like bricked, like the definition of bricked, almost. Because we had like such a bad penalty. Or we could have gotten at least over 6,000 points and a better rank. But that's in hindsight. If I hadn't written a wrong solution for E, it would be better, but I did. Nothing I can do about that. So that is it. Still a good rank. Despite all the mistakes, it's still a good rank. So we'll leave it at that. And with 3 minutes left, I'm going to go over the solutions to the problems I did solve, and not really going to go over F. I made it very unclear what I was thinking about, but at the same time, like, it didn't really lead anywhere, supposedly, because I don't know how to do this final part, so this whole solution might be a bust, or this could be exactly what you need to do, and I don't know. But the basic idea is, once you can solve this problem, then it's like, you want to find the answer for the subsets where the GCD is greater than 1. So let's find f of g, that's like, it's not composition, f of g, where g is a certain GCD value, and then the answer is the sum of all minus the sum of f of g. finding f of g itself is actually hard, but finding f of finding the sum of f of x, where x is a multiple of g, so g divides x, we say, is easier. Because then you can put all the multiples of g into like this group, and then you can solve the problem for this group. And then you can find the thing, you can find the sum of all multiples of g. And then f of g is equal to this minus f of all multiples of g, excluding g itself. Because like it's just the GCD of like all the multiples, like you just subtract all the multiples, and so all you get left is f of g. And by harmonic series, whatever, yeah, it's just harmonic series stuff. It's the sum of it's the sum of n over I is the number of elements you end up solving for, which is O of n log n. So that part will be fine. The problem is solving this. If we can solve this in O of n, or O of something that's close to O of n, then we're going to be fine. But I don't know how to do that, and that's where the bottleneck is. So that's my sketch for f. Of course, it doesn't lead anywhere, but that was the idea I was trying to pursue, which ended up not working out. Okay, so final rank is pretty much set in stone. Ouch. Yeah, there's a lot of rating loss here. This one, because it's a new account, it's different, but still, not a friendly round. Okay, I'm going to proceed to totally ignore f and just like continue this. Alright. Alright, I'm gonna not read statements because you did the contest probably, and there's a screencast, so I believe in you. I'll assume you know what the statements are. Okay, so like this sum is kind of peculiar. Let's consider some array. For example, 01, 01, 2, 3. Did they just say it can be shown? Okay. Now consider this, consider like the sums we're going to take. The first sum is going to include the first 4 elements. The second sum is going to include the last 3 elements, or the last 4 elements for this. This is going to include the last 2 elements, and this is going to include the last element. So how many times is each element considered? Well, this is 1, this is 2, this is 3, and this is 4. So specifically, the number of times we include an element is equal to its index, I. And we're taking the sum each time we consider the quantity ai over I. Which means that if we take each element I times, and we take the element ai over I times, it means the total sum is just the multiple of the number of times we take an element and the element itself, which is ai. So what it means is no matter how you reorder the elements, the sum we're interested in is going to be the same. Specifically, the sum we're interested in is the sum of ai, and we can't change that no matter what we do. So if the sum of ai is already equal to m, then we're automatically done, and the answer is yes. Otherwise, there's nothing we can do to change the sum, so the answer is no. Okay. Now we can do b. Might fail system tests, I'm not actually sure. It's possible. Because people are being hacked on C. Okay, so my idea for B is, well, there are many ways you can do this, actually. Actually, there's a very easy way to do this. What I did was kind of overcomplicated, to be honest, but there's a very easy way to do this. Yeah, I don't know why I did what I did. That was kind of dumb. Wait, does that work? I feel like it doesn't. What am I thinking? Okay, I'm going to draw out a 5 by 5 matrix, and this pattern is just going to speak for itself. So I'm going to go over the very easy to think of, or the very easy to write solution, and then my solution, which is kind of sketchy and probably, I know it works, but it's sketchy. So consider this matrix. You put a 1 here, 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 put a 1 here. Right? Now look at this row. It has 2. This column has 2. This row has 2. This column has 2. This row has 2. This column has 2. This row has 2. This column has 2. The only row and column that doesn't have 2 are these two. So we can put an extra 1 in this corner. And they said in the clarification that we can have numbers be 0, right? Yeah, non-negative integers. Which means that with the rest of these, we can put in 0, because we're just allowed to do that. So let's do that. And then notice that the sum of each column and each row is just 2, which is prime. 2. So this construction will work for any n. Because 0 and 1 are not prime themselves. So the only degenerate case we ever end up having is a 2 by 2 matrix, but in that case you would actually end up doing the same thing. The original streak of 1s would go like this, and then you would have the extra 1 you force in the bottom right corner, or bottom left corner, so either way you would still have 2s. So no matter what, for any n, this construction will work. What I did was something weirder. I did something like, let's just do the 3 by 3 matrix, like so. And basically, I did something with the diagonal. So I put 2s everywhere, just to create some sort of offset. And then I put some number x, where x is not prime. Actually, I think I put 1. No, I put 1s here. Yeah, these should all be 1s, not 2s. So x is composite, but notice that every other element is going to have n. Notice that the sum of every row and column is going to be n minus 1 plus x, because you have x in every row and every column, and everything else is 1, and you have n minus 1 1s. So n minus 1 plus x must be prime. It turns out this number always exists. So, or at least for the given constraints, this number x always exists and is easy to find. So I just found it by like generating all possible small primes and just looking at them. I don't recommend that one. The one I did just before is easier, probably both to think of and to just do. So, yeah. Oh, and the way you can do that is, for example, consider this matrix. The original construction, you want to put 1s on this diagonal, and here. So this you can do explicitly. This is all cells where I is equal to j, and this is all cells where, so for example, this is row, this is 0 and 1, and this is row 1, column 2, meaning that this diagonal is all cells where I plus 1 is equal to j. So for either of these cells, and explicitly the bottom left one, you can check for these two conditions, and if so, put a 1, otherwise put a 0. So that's a possibility. Okay, this one is kind of like, I spent like 10 minutes solving a version that was misread, which was like much harder. And then I just like, it was sad. I wasted so much time. Because the real problem is a lot easier than the one I was solving. Or I will fail system tests. One of the two, mutually exclusive. But system tests aren't even happening yet, so don't know what's up with that. Anyone else solve F? Just those two guys? Yeah, like an LGN, and it's pretty good of an LGN, I would say. So consider what's happening in this algorithm. Right, we want this position, say this position is like here. So we can kind of just simulate the binary search and see what needs to happen for us to get here. Okay, so the first position is we just like compute it. It's here. So we ask what number can be here. Let's say we're going to put some number y down. And this is position P, and of course we have n. So let's say we're going to put some number y down. What I was doing is I was solving for finding x in any possible position, not all positions, which was, I think, harder. Or any possible position, not a fixed position. Actually, it's not even that much harder. I just kind of overcomplicated everything. I think that's what happened. Yeah, I just overcomplicated everything. Okay, I don't know what I'm thinking. That whole thing was stupid. But let's say we want it to end here, then what can y be? So there are three cases. Y is less than x, y is equal to x, and y is greater than x. What happens in this? So if y is less than x, then the binary search will think that x... What the hell? Where's my mouse? The binary search will think that x is to the left. No, wait. Yeah, we'll think that x is to the right, right? Like if this is less, yeah. So we'll think that x is to the right, which we don't want, because clearly we want x to be in this position. So the binary search has to think that this is the valid range. So if this is the case, there are no answers. So like this can't be true. And if y is equal to x, then we'll stop immediately. And actually it's equivalent to saying less than or equal to. But x can't be here because it has to be like, x has to be here. And it's a permutation, so we can only put it in one place. So it can't be equal to x either. And if y is greater than x, then that's the only case in which it'll think the range is actually correct. So this is right. So we have to put down some number y that's greater than x. And how many numbers can we put down? Well, this is a number that's initially n minus x, and then after you put one number, obviously it becomes like less than that. So n minus x minus 1. And if you continue, then it's like chill. You just like keep on subtracting these numbers. And so you have n minus x possibilities to put down a number y which is greater than x, and then you have n minus x minus 1 remaining numbers. So currently the answer would be m minus x. Okay, now we're going to move, now the position moves over here. Let's use a different arrow and a different value of y. Yeah. So now we do the same thing. But now we want y to be less than x because we want the range to be this. So we need the number of y that's less than x, which is x minus 1. And then it starts at x minus 1, and then it just gets lower. So now the answer is n minus x times x minus 1. And now we have that the position is here, which is exactly here. So we need this. We have one possibility for this. And then once we do this, these 8 numbers that we haven't touched can be whatever they want in any order. So say we had like k numbers remaining, then it's just k factorial. Because we can permute these numbers however we want, and we have k numbers to put down. So after k turns, or yeah, I guess after k turns, it would be m minus k factorial, or you can think of k as the number of remaining numbers. However you do it, it's just something factorial. So I think that is the idea. You kind of just simulate the binary search and don't fail system tests, ideally. I want to see the hacks that happened. But whatever happens, that's what happens. Indeed. So the conditions for wanting this to be true is essentially, say you have the position P and then the current middle is M. Then if P is greater than M, which is, so for example, this is M, this is P. If P is less than M, then you want it to go to the left, which means that you want Y to be greater than X so that you think it's on the left. So if P is less than M, then you want this case. If P is greater than M, then you want this case. And if P is equal to M, then you want this case. So these are the cases you consider when you figure out what element you have to put down. And notice that if any of these counts ever become 0, then the whole answer will be 0, which it has to be because there's no possibilities. So you don't really have to worry about that casework, I think, unless I'm going to fail system tests. But no matter what, the answer will become 0 at some point, even if you end up with negative numbers or something, because it's 0. So that's my idea. We kind of leave it at that. Yeah. Let's see. At some point, we will maybe not fail system tests, or maybe the system test will start at some point. If I do fail system tests, I guess I'll comment on it later. Okay, this one probably... I don't know, this was not, like, in terms of my perspective, this was not a bad div 2. I just screwed up almost every problem, which is sad. That shouldn't have happened, but it did, unfortunately. So that's what's happening there. So that's cool. But this is a problem on a tree. And once again, I'm not going to read statements. So basically, consider any tree. I'm pretty sure I drew some like very big tree for something, but it's not that big a deal. Do it like this. Ba-bam, ba-boom. We got a tree. I'm gonna check my system test. I don't actually have to be anxious because this isn't rated for me, so I'll leave it as is. Okay. Right, so essentially consider like all of the citizens. Eventually they're all going to end up in leaves of the tree. And all the citizens that would end up in a specific leaf, if the bandit goes to that leaf, they will catch all the citizens that end up in that leaf. So it essentially becomes like the aspect of time doesn't matter. You can reorder the moves because the bandit doesn't do anything until the end. It's the same as reordering the moves such that all the citizens first go to any leaf in the subtree of the place they're at. And then the bandit will take the leaf with the most amount of people and capture all the people there. So this aspect of time they use doesn't matter. It's really just, also this is directed, I guess. Although it doesn't really matter because it's a tree and you can only go down to children. Yeah. So, by the way, this implies that it's a tree, that there are n-1 edges and that it's connected. So, it's also enough to have n-1 edges and be acyclic, or be connected and be acyclic. All those three conditions imply that it's a tree, and they also imply each other if you have at least two of them. which is kind of cool and also kind of unnecessary. It's more about reading statements and understanding the conditions for a tree. But yeah, I don't know why they refuse to say it's just a tree in many of these statements. Also, having exactly one parent also implies a tree. That kind of structure. Anyway, going off on a tangent here, as always. So, consider like this subtree. Actually, let's say everything's in the start. Like, let's say we have like 50 up here, and then everything else is 0. So, like, the bandit's gonna pick the leaf that has the most. So what we want to do is evenly distribute it as evenly as possible so that the maximum is as small as possible. And so the answer for this specifically is 50 over the number of leaves we have, which is 6. That's the like maximum we're forced to have, because say we like put down 8 in all of these. Right? That's totally even. But now we have 2 left. We have 50 minus 48, which is 2. And so now we have to put these 2 somewhere. So we have to increase some of these by at least 1. And so to continue the evenness, we make 2 of them 9. And thus the answer, it becomes the ceiling of the total sum over the number of leaves. But this is true for any subtree too. For example, say I totally ignored this. We had 0 everywhere else, and we had 50 here. Then this would be the ceiling of 50 over 4, because this subtree in itself is like an independent problem. So, but there's another case too. Say we have 50 here, which means that both of these leaves will end up getting 25. And then we have like 12 here. Obviously, we can't evenly distribute these, because if we give all of these 2 from the root, then the answer is going to be 27. But if we instead decide to put everything from the root into this subtree, for example, distribute it like this is a 12, then the answer will be 25, which is better. And so the problem is sometimes we can't even get the even distribution. But in that case, notice something, that say we had the total sum is 62, which means that the even distribution would be 10, 10, 10, 10, 11, and 11. So say we had this even distribution, but we actually think of it like this. We have these two 25s here, and these are bigger than these, which means that like we can kind of do anything we want to these as long as we make sure they're not 25. So we can make it so all of these numbers are less than or equal to 10, and it's kind of just like filling in space. Because here we used as much space as possible like in each number. But here we have extra space that we've already used. I'm trying to find a way to word this that's like not terrible. But like here we have 12, and the worst case for these would be that we have 40 in here, but we don't. We have 12. And we can kind of do whatever we want with this 12 to this side, because we already have like the worst answer on this. So what I'm saying is, in a convoluted way, is either we can evenly distribute, or we have something that's already bigger than the even distribution. But if we have something that's already bigger than the even distribution, then because the even distribution is a smaller answer, we could just do a similar thing to the even distribution, assuming we don't touch the big one, and therefore the big one will be the answer. Like in this example, for example, we have 25 in each of these. And so we have this 12. And we can do whatever we want with this 12 as long as we keep it to these and we keep them less than 25. So essentially, because this is bigger than what we would get from the even distribution, This is automatically the answer, and we don't really care about how we distribute these. Okay, my whole point that I'm trying to make with this is for a specific subtree, which could possibly be the whole tree, there are two possible answers. It's either the maximum of, it's either like the worst case is one of the answers of the subtree of one of the children. So it's the maximum over all, call it like f of x, then f of v, which is the answer for a subtree, is either, is either going to be like one of the children is too big to do the even distribution, meaning that it's the maximum of all of the children of v, like the maximum answer, or it's the even distribution itself, which is sum over leaves. And it comes down to this recurrence, that the answer for a subtree is either the maximum over all children of v, or the maximum of the answers of all children of v, or the even distribution, which is the sum over the leaves. What I've been trying to say is, if some child is too big, then the even distribution used more than we thought we would need to use. No, that doesn't make any sense. I'm saying that these are kind of independent of each other. That's what I'm saying. So either we have the even distribution, in which case the numbers are close enough together such that we can do it, or we don't, and then the numbers are far away from each other, and we have some big one, and then this would take over anyway. So these are independent of each other, meaning that this recurrence works, because if we assumed we did the even distribution here, but then we don't actually want to evenly distribute it when we go up to this one, that's like fine, because we can redistribute it kind of, because it doesn't matter. We're just looking for the optimal answer, not specifically like how we're doing it, I guess. So this is the answer. It's like a tree DP, or dpv is equal to the maximum of the dp values of the subtree of each of the children, and it's the maximum of that and the sum over the leaves, the ceiling. So I guess I can go over code on that, where it's like, it's just straight up this. You keep track of the number of leaves, the sum, take the maximum, and then consider that with the ceiling. How are the things going? Okay, we got A, yay. System tests are kind of slow too, aren't they? How are we doing on A? Nice. We have a slow A. Whoa, hack. Hack on A. How would you get a hack on A? What did this person do? Some mod. What did they do at mod? Oh, that's sad. I guess pretests were weak in terms of that. Although it is definitely hard to catch all of the weird solutions that would somehow pass pretest. So it's not like criticism. It's just that it didn't catch that specific solution. But a hack did. How many system tests were there? Would I know? I wouldn't know. Would I? Could check the M site, but I don't care that much. Okay, so that's D. Basically, it comes down to a simple tree DP. That's how I solved it so fast. And E is more fun. E is essentially, you got some like stuff going on. Okay, so we're gonna solve all of the problems simultaneously of does there exist a subarray such that like the mex of L and R is equal to K? We're going to solve this problem. For all K, does there exist, like over all possible values of K, we're going to solve the problem, does there exist a left and a right value such that the mex of that subarray is equal to K? Okay. Now, consider the element K itself. Any subarray, let's consider an array with some K's in it. Any subarray that has K in it automatically doesn't have the mex of K because like if the mex was K, then the subarray would contain K, meaning that the mex has to be greater than K, so the mex can't be K. And like it's just not K. So we can't contain K. But we can contain anything else. For example, say we have K plus 1. Because the mex isn't K, the mex is less than K. Or because the mex is equal to K, then this element won't affect anything. And we can also have elements less than K, which we want anyway, because the mex can be less than K. So basically, like the more elements, like as long as we don't have any K, it's just as good to have as long a subarray as possible. Because either new elements won't hurt you, they won't affect the mex negatively, or they will make it better. Like they'll help you. For example, say we have K equals 3, and then we have this array. So we want the mex to be 3. Say we have 1. And then like say we add in a 7, and that's not going to affect the mex. If we add in a 3, it does. But if we add in like a 4, it's also not going to affect it. If we have a 2, it's going to help us. Or if we have a 1, it's not going to affect it. If we have a 2, it's going to help us. So what I'm saying is, as long as we don't have K in the subarray, it's optimal to make the remaining subarrays that don't have K as long as possible, which means that they'll be in these gaps between the Ks. For convenience, if you want, you can kind of simulate sticking a K at the beginning and at the end. Which means that in terms of checking if there exists a subarray with the mex being equal to K, it's enough to only check these gaps. So you only have to check these subarrays, possibly including the beginnings and the ends. So we'll consider these virtual Ks, where we stick them in to make implementation more convenient. Virtual Ks, yeah. Okay, how many such subarrays do we have that are between the elements? Well, each element splits one subarray into 2. So this green subarray will become these 2 now. And there are n elements, which means that because each element only creates one more subarray, we have O of n subarrays in total. So if the mexes of any of these subarrays is K, then this is true. Hopefully you see how with this information we can easily get the answer. But now we have O of n subintervals, and now the only question is, how do we check the mex of a subarray? Because if we can do that efficiently, then we're done. And well, we can use the magic of offline queries. And the way offline works is you basically answer all the queries in a certain order, an order that's convenient to you, because we already know all of the queries beforehand. We know we're going to ask for these 5 queries like as intervals. And we know about all the other queries we're going to make too. So like, cool, right? So we have a bunch of intervals, And we basically just want to ask what's the max on each of these intervals. And we can generate these intervals beforehand and solve for all of them offline at the same time. That's the idea. So now that we have these intervals, what do? Well, we ask, let's sort these intervals by their right point. This is the point where I consulted Stack Overflow, read something in 5 seconds, and then closed it, which was probably confusing to everyone, but this is what happened. So let's sort these queries by their right interval, possibly having multiple at the same point. Okay, now, this is kind of confusing. So let's say we're solving for a single interval now. Basically, consider the elements like 1, 2, 3, 4, 5, 6. We want to know simultaneously if we have all of these in this interval, which is basically saying, does there exist a 1 such that L is less than or equal to this position of 1, which is less than or equal to this position of R. So we're solving for R like in increasing order of right points, which means if we make it so we only consider this prefix, automatically we have this condition satisfied. So now we're only interested in, is there a 1 that's greater than or equal to L? And so what we can do is for all elements only on this prefix, we can store the rightmost index of a 1. So say the array is this: 1, 3, 2, 5, 1, 6, 4, 5. Being careful here. And these are indices 0, 1, 2, 3, 4, 5, 6, and 7. Then when we move here, the rightmost position of 1 is 4. The rightmost position of 2 is 2. The rightmost position of 3 is 1. Rightmost position of 4 is 6. 5 is 3. No, 7. And 6 is 5. And if we had some other element, we can make it something like -1 if it doesn't exist. Okay, now why is this useful? Because now, on this sort of array of rightmost positions we have, and also if we get some other element, for example, like we get another 1 somewhere, then we would just replace this 1 with whatever the new position is. And we do that as we sweep to the right. So now that we have this, for this specific interval that ends at this point, we just need to figure out what its max is. But on this array, what we can do with this is we want to find the leftmost point such that its value is 1. It's the leftmost point such that, or not 1, sorry. The leftmost x such that the position itself is less than L. In that case, this including -1s because we have all the elements initially not in the array over here. And then if we can find the leftmost x less than L, which is in this case this one, then that's the smallest element. Leftmost is smallest because these themselves are values. Then this is the smallest element that's not inside the range, which is exactly what we want. So there are many ways to do this. You can, for example, build a segment tree on these values and just simply binary search over it with range minimum query or something. So that would be O of log squared of n, which is fine. Or you could do even better and how's this doing? 77 milliseconds. Okay, yeah. So I think that will probably pass. Although it's kind of sketchy because the time limit is not great. But there's something better you can do. And it's kind of a similar idea to something I described in the Raif round. I think that was what it was. Let's say you have these segments. You have this big segment, and then it splits into these 2 segments in the segment tree. Now we know the RMQ of this range, this whole range is -1. We know the RMQ of this range is 1, and we know the RMQ of this range is -1. And we're looking for the leftmost element less than 3. So let's consider this segment, right? Now, consider this left half. It has a value less than 3. That's guaranteed, because the minimum value on this interval is 1, which is less than 3. Which means that we don't need to look at the right, because we already know there's a value that we're looking for on the left. This is the whole principle of binary search, that we cut this range in half that we're solving for. And then we look within these further segment tree ranges, let's say it's like this. Then this RMQ, this minimum here is 2, and this minimum is 1. So since we're looking for an element less than 3, we'll go into the left again, because we know we have something less than 3 on the left. And then here we do the same idea. Different color, that's not anything we've used. Yep. Then here, the RMQ here is 4, the RMQ here is 2. So 4 is bigger than 2. 4 is not less than 3. Meaning that whatever we're looking for, it's not on this side. So instead it means it's on this, it automatically means it's on the right. Because we know there's something in this interval, and we know it's not on the left, so it has to be on the right. And once we get to a single index, we're done. So basically, that's it. We do the binary search, except we do it inside the segment tree itself by looking at the values. And because this is just querying elements of trees, which we already know, this in total is O of log n per query. In terms of my code, I guess I can look at that, although it's very simple. So if you have one index, just return that index, otherwise compute the mid. If the left is less than the value, if the minimum on the left is less than the value, go into the left, otherwise go into the right. And this is a special case. If all of the values are... This would only happen on the full interval. But say you have something where all of the values are greater than or equal to 3, for example. Then for convenience, you can have it return the index just outside. Because that would mean that if you have something like this, say the input is 1, 2, 3, 4, 5, 6, 7. Then the mex here will be, well, this subarray has mex 1, sure. This subarray has mex 2, this subarray has mex 2, this one has mex 3, this one has mex 4, etc. up until the whole subarray having mex 8, so the mex itself is 9. But this setup will only find it up to 8. So what we need to do is, if the whole subarray is contained within the mex, then we return a position that's 1 greater, which means that we'll account for this case. So that's why I do, if tree I is greater than or equal to v, return tr plus 1. And you should generally test with a case like this just to make sure it works out. So this is how you would do it. You would first find all these intervals that you need to solve for by just solving for this problem. And then once you do that, you can solve all these intervals offline by doing this trick. This trick of binary searching within the segment tree and keeping track of the rightmost position of each element. There's one special case when everything is 1. In this case, there's no subarray that has mex 2. Or there's no subarray that has mex 1 because you have to consider non-empty subarrays, as they put in bold. So if everything is 1, the answer is automatically 1. And I think that kind of breaks the solution because there's problems. Checking for 1 explicitly is annoying doing it this way because there are no elements less than 1. So it just kind of doesn't work out in the same way. But for all other elements, you can do it this way. There's just a specific check to see if all elements are 1. If so, the answer is 1. Otherwise, there's some element that isn't 1. For example, say we have 1, 1, 1, 2. And the mex of this subarray is automatically 1 because it doesn't have a 1 in it. So the answer is at least 2, which means that you can do this. Okay, and obviously once you have this information, it's just answering the smallest k such that this is not true. Which is at most n, so it's just whatever. Those are my ideas. Those are my solutions, the ones that I submitted. Hopefully they don't fail. C is in queue. Yeah, okay. So I'll leave it at that for now. Ended up with a really bad penalty on these. Oh, jeez. There are system test fails. Is it ever going to get to mine soon? I guess we can check. Status. Mine took a long time. Okay, it's not going to get to these anytime soon. So I'll end the screencast here. If I'm wrong, I'll just like figure out what was wrong and put it in the description or something. Okay. Go over upcoming contests. I'm not going to do this live for multiple reasons, but I will stream it, I guess, something like that. I might stream. It depends on other things. But it's likely that I will. So in this case, I'll stream something like the Div 2 version, and that's what's coming in the future. Yeah, there's no way it's getting to my solution soon. So, wait, how far does it get? It's actually not that bad. Okay, whatever. I don't want this to be too long. So if my C is wrong, I'll just like put in the description or something what happened. Okay. Yeah, that's it. Goodbye.